So some other ways that we can use second degree Taylor polynomials. So we're going to be given that the second degree Taylor polynomial is given by, our standard version of a quadratic, right? It's just a little backwards. Usually we think of a as being the coefficient of the x squared term, but it doesn't really matter. They're just parameters, right? They're just variables standing in place of numbers. So we are centering our Taylor polynomial around x equaling 0. So our c value is 0. So all we want to do is we want to know about the signs of a, b, and c if it has it pictured below at x equaling 0. Right, so if we're looking at x equaling 0, so remember that a is equal to our f of 0 value, right? So at f of 0, right, which is greater than 0, so we're going to be able to say that a is positive, right? We're going to write that a is greater than 0, right, since f of 0 is positive. Right, for our b value, right, b is equal to our first derivative at 0. Right, so our first derivative, we go ahead and draw that tangent line here. It looks like our function is increasing over this integral, right? So our first derivative is greater than 0, so we're going to say that b is also positive since f of x is increasing at x equaling 0. So the first derivative at 0 is greater than 0. And then our last value here, I guess we'll use purple, right? So c, right, the number in front of x squared we find by finding the second derivative at 0 and dividing it by 2 factorial. So our second derivative at 0, right, that deals with the concavity. So our function is concave down at that function value, right? So we're going to say that this is negative. So c is going to be less than 0. Since f of x is concave down, at x equaling 0. So our second derivative at 0 is less than 0. So our second derivative at 0 divided by 2 factorial is going to be less than 0 as well. Okay, we just have a little bit more on our note packet to cover about Taylor polynomials, so I'm going to try and cover all of this in one video, right, because we got one more page. We don't need to split this up again. So sometimes we can create Maclaurin polynomials, which this is spelled wrong. Great job. To approximate functions without having to derive them using Taylor's theorem. So we have some very common functions that we're going to be looking at, and so these are going to be really great ones to memorize. So if you develop them once and then kind of memorize the patterns because they come up a lot, then we can use the ones that we know for Maclaurin polynomials to kind of modify them as we create other polynomials around different values. So we're going to list the first 4 non-zero terms of the Maclaurin polynomials for the functions below. So the first one is sine of x, which we have done sine of x before, right? So I'm just going to look up, right, sine of x, we actually did it at the first page of this packet. So sine of x is going to be approximately equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, right? And if you're not positive about that, right, when we flip back to what we did up here, Maclaurin polynomial on c equaling 0 for f of x equaling sine of x, we only went out to the first 3 terms, right? But you can kind of see what the pattern would be as we kept going, right? We have also already done e to the x, which I'm going to put over here. Right, e to the x we did on the previous page. For those of you who've been following along, right, we can see what's happening there. Right, it's just, they're all positive ones, pretty easy. So our first 4 terms are actually right there for us, Right, so I'm going to actually just copy and paste it. Work smarter, not harder, right? So we can say that e to the x is approximately equal to this guy. The only one that we haven't really talked about here is cosine of x. Right, so going off to the side real fast, I'm just going to say, okay, well, we got f of x is cosine of x. And if we're going around 0, that gives me a 1. My first derivative is negative sine of x. So my first derivative value is going to be 0. Right, then I get negative cosine of x. Right, and we want the first 4 non-zero terms. So derivative of negative cosine is positive sine. Right, so far I only have, 2 non-zero terms. So I would have to keep going, but maybe you can kind of start to see the pattern here. Right, so if we noticed that the sine of x zeroed out when we had an even power on our derivative, whereas cosine is going to be the opposite of that. We're going to zero out on the odd powers of the derivative. And we're just going to we can do this all longhand for this one. Hopefully you kind of see what's happening. Right, so now I have 3 non-zero terms, so I need to go out to the 6th degree if I want 4 non-zero terms. Sorry, I'm a little distracted. Right, so if I use that to kind of put this together, and I'm going to have to go back and make that smaller, we get that the cosine of x is approximately equaling to, well, f of 0 is 1, and then this would be our first degree term, so we have no first degree term, and then we have a second derivative value, so that's going to be 1 minus 1 over 2 factorial times, x squared, so we're just going to get 1x squared in the numerator there. My third degree term is a 0, so that's going to go away. My fourth degree term is a positive 1, so I'm going to get plus 1x to the 4th over 4 factorial. And then my fifth degree term is a 0, so that's not present. And then my sixth degree term is negative, so I get negative x to the 6th over 6 factorial. So I'm just going to make that a little smaller here to kind of give us some space. So these are 3 things that you definitely want to have memorized because we can use them to kind of manipulate other things. And I am so sorry because there's going to be some barking probably because I think there's a squirrel on my back porch and my dogs really love squirrels. Okay, so we're going to use these couple of things to manipulate Maclaurin polynomials for other functions. I am so sorry. Okay, so we're going to do sine of x first, sine of 2x rather. So sine of x we can see up here, right? So then sine of 2x is going to be approximately, we're just going to plug 2x in for all of those x's. So we're going to get 2x minus 2x cubed over 3 factorial. Tofu! Shh. Plus 2x to the 5th over 5 factorial minus 2x to the 7th over 7 factorial. In theory, you could leave it like that. If you want to simplify it, that's going to equal 2x minus 8x cubed, and then 3 factorial is 6. I'm actually just going to leave the factorials in there. Plus 2 to the 5th is 32x to the 5th over 5 factorial, and then 2 to the 7th is 128. So x to the 7th over 7 factorial. And you could simplify with the factorials if you wanted to, but you don't have to. Okay, so for x times cosine of x, we know what the Maclaurin polynomial approximation is for cosine of x, so this is just going to become x times, not going to use an equal sign though there because we are approximating them, times the cosine approximation. I am so sorry. Please bear with me. I'm too far in to stop this recording and have to redo it. I only have so much time in the day. Right, so just copying down my cosine approximation, which in the future I would have memorized because we're going to be using them a lot. And then it's just distributing the x. So we get x minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial, right? And if I were to go through that Taylor polynomial process, I would get the same thing. But you always want to build as you go, write out the original function first. Don't try to do everything in your head, because if you can show this step correctly, then it's easier to not make as many mistakes, and you want to show that that conceptual knowledge is there, especially on the AP exam. Okay, so then we have our last one. So we're going to build as we go. So I have a 4 on the outside. And then my e to the x function, right? If I look back up, it's 1 plus x plus 1 over 2 factorial x plus 1 over 3 factorial x cubed, and so forth. So I have 1 plus, instead of x, I'm going to have x squared plus x squared squared over 2 factorial plus x squared cubed over 3 factorial. Right? So that's going to equal 4 plus 4x squared plus 4x to the 4th over 2 factorial plus 4x to the 6th over 3 factorial. If you really wanted to, right, you could simplify it. You don't have to. We have 4 plus 4x squared plus 2x to the 4th